Archimedes was born in 287 BC in the city of Syracuse. His father Phidias is believed to have been an astronomer and a mathematician. We don't know much else about his family, but there's been evidence that he was the nobility of Syracuse and was actually related to King Hero II, who was the king of Syracuse. Archimedes traveled to Alexandria for his studies. He studied at a school that was established by Euclid, and Euclid's elements are believed to have a large influence on Archimedes' works. Archimedes returned to Syracuse and lived out the remainder of his life. He devoted time to studying multiple fields of science and research. Archimedes was known to send statements of his theorems to his friends in Alexandria, but never gave proofs of his statements. Mathematicians would sometimes claim his work as their own, so the last time he shared his works with them, he also sent out 2 theorems that were false. And he said, so that those who claim to discover everything but produce no proofs of the same may be confuted as having to pretended to discover the impossible. Archimedes constructed various machines and made several discoveries to solve the various problems of the king. One of these was the Archimedes screw. King Hero had ships that had their holes filled with water. The king called upon Archimedes to find a solution. Archimedes created a machine that consisted of a hollow tube, and inside the tube was a spiral that could be turned by a handle, and it would actually bring the water up and out of the screw, and it would bring all the water out of the ships so that they would be dry. We actually still use that today in developing countries for irrigation, and it actually helps to move grains and coal. There was also the claw of Archimedes, and several of his things were to protect this city from the Romans. The claw would come up and come down on the ship, and it would force it down into the water. Then he also created the death ray. One of Archimedes' favorite areas of studies was optics. And it was in these studies he came to be known as this heat ray. He arranged a large group of mirrors, most probably polished seals, and when the sunlight was concentrated by the mirrors, it would theoretically catch the approaching ships on fire. The actual likelihood of that has been debated. One of the most well-known stories of Archimedes is with him running through the streets naked, screaming Eureka. And what this had been based upon was King Hero had asked Archimedes to discover whether or not his crown was made of pure gold. And Archimedes couldn't quite figure out how to do this, and he had thought on it for a while. And then one day he was getting into his bath, and he realized that the further he went down his bath, the more water was coming back out. And so that gave him the idea to submerge the crown down into the water. And if he saw how high the water had risen, then that would tell him the actual volume of the crown, and from that he could find the density and know whether or not the king's crown was pure gold. This is now what we call the Archimedes principle, or the law of buoyancy. Archimedes was greatly recognized for his inventions during his lifetime, but his mathematical contributions are what's led him to being regarded as one of the greatest mathematicians of all time. Many of Archimedes' works were lost in the fires of Alexandria, and so the only works that we have were in Latin and Arabic. Archimedes explained the law of the lever, used it to calculate areas and centers of gravity. He found the area of any segments of parabolas that has been cut off by any chord. He defined what's now known as the Archimedes spiral, and it was the first mechanical curve that was ever considered by a Greek mathematician. Archimedes proved that the relation between the area of a sphere to that of a circumscribed straight cylinder is the same as the volume of the sphere to the volume of the cylinder. He also described a method to cut a sphere by a plane so that the ratio of the segment's volumes comes out to be a specific desired value. Archimedes calculated the areas of volumes of sections of cones, spheres, and paraboloids. He also discussed the law of equilibrium of fluids and proved that water will always adopt a spherical form around a center of gravity. He also calculated the equilibrium positions of sections of paraboloids. And on floating bodies, Archimedes actually described his Archimedes principle. Archimedes proposed a number system that would allow him to express numbers up to 8 times 10 to the 63rd, and argued that this number was so large it could represent the number of grains of sand fitting inside the universe. Archimedes created a method to make calculations that we would consider today to be integral calculus. He proved the ratio of a circle's circumference to its diameter is the same as the ratio of a circle's area to the square of its radius, and he approximated this value to be between 3 plus 10 over 71 and 3 plus 1 over 7, but he did not actually call it pi. Archimedes had held off Roman attacks for many years, but in 212 BC, the forces of Marcellus overtook his city. It's been well documented that Marcellus had a great respect for Archimedes, and for that reason, Marcellus had dispatched his soldiers to find and deliver Archimedes to him unharmed. The exact details regarding his death is unknown, but the leading theory describes Archimedes was so focused on a mathematical problem that he had not realized the Roman army had stormed the city, and upon the soldier's arrival, the soldier had instructed Archimedes to accompany him to Marcellus. Archimedes just simply refused and went back to working on his circles, and it's believed that the soldier flew into rage and struck Archimedes dead for that reason. Marcellus was greatly upset by Archimedes' death and ordered Archimedes to be buried with full honors, and as Archimedes had wished, his tombstone was engraved with an image of a spear within a cylinder. So what we're going to do today is Archimedes' proof of the area of a circle. And in measurement of the circle, Archimedes said the area of any circle is equal to the right-angled triangle in which one of the sides about the right angle is equal to the radius and the other to the circumference of the circle. Archimedes employed the method of exhaustion to do this proof, and he arrived at it in 2 different parts. But first, we're going to look at our circle and our triangle. So this is our circle with our radius r, and that is the same as the length for the height of our triangle. Then our circle has a circumference, c, that is the same as the length of our triangle. And what we want to do is prove that the area here is equal to the area here. So we're going to do that in 2 parts. The first part, we're going to work with inscribed polygons. And to do that, we're going to be using C as the area of our circle, T is going to be the area of our triangle, and P is the area of our polygon. Our first case says that the area of our circle is greater than the area of our triangle. And based in Euclid's Elements, we have various claims, one of which is the claim that the area of our polygon inscribed within a circle is less than that of the area of the circle. So that would lead us, if we're basing and trusting that claim and trusting our case, that the area of our circle minus the area of our polygon should be less than the area of our circle minus the area of our triangle. But also based in Euclid, we have that the area of our polygon is less than the area of our triangle, which would lead us to believe that the polygon is less than the triangle is less than the circle, and overall would give us that the area of our circle minus the area of our triangle is less than the area of our circle minus the area of our polygon. And so these two are obviously contradictions of each other, and so that means that case 1 can't possibly be true. So that leads us on to our second case, and this time it's using circumscribed polygons. And for this one, we're going to say that the area of our circle is less than the area of our triangle. Another claim that's based in Euclid's Elements is that the area of our triangle is less than the area of our polygon because the triangle is inscribed within the polygon. This would lead us to say, based upon our circle being less than our triangle being less than our polygon, that our polygon is greater than our triangle, and both are greater than our circle. This would lead us to say that if we took our triangle minus our circle would be greater than our circle minus our polygon. This, canceling both of our c's on each side, would eventually give us that P, the area of our polygon, is less than the area of our triangle. But this is a contradiction to the first claim that we know from Euclid has to be true. And so we know now that case 2 can't be true. And so if C is not greater than T and C is not less than T, that C has to be equal to T, which is just what Archimedes had said, and that is the end of his proof.